Hello, my name is Zhang, and this is Lab 2, Motion of a Falling Object. The motion of an object can be described using Newton's second law and the net force acting upon the object. Newton's second law is described as the change in momentum over time. Since mass is constant, we can factor the mass out so that it would be mass times the change in velocity over the change in time to find force. However, the net force is computed by the total forces acting upon the object. In this case, both the force of gravity and the drag force affects the object, so the net force will be the sum of these two forces. The net force is used to update the velocity, while the updated velocity will be used in the position update formula to determine the position time graph of the falling object. The primary objective of this lab is to investigate the motion of the dinosaur toy as it falls through the air, considering both gravitational and drag forces while using tracker to experimentally determine the y position over time and glow script to computationally determine the position with gravity only and both gravity and drag force together. The experiment here is the dinosaur toy being dropped from rest, and it's dropped from rest and it doesn't have any initial velocity nor position, since the position here will be starting at 0, 0 and falling down in the negative y-hat direction. The system here is the dinosaur toy, and the surrounding will be anything around it or surrounding it. In this glow script code, this is to determine the y position over time for when net force is only gravity. And so initial positions here the initial conditions here have position and velocity being at 0. The net force is only gravitational force, which is computed with negative mg, and the j-hat position, which j-hat represents the positive y-axis, and the mass here is 0.0635. The only difference between the previous code and this code here is this code introduces drag force. So in order to determine the net force here, you have to add the gravity and the drag force together and use that to find your velocity and then finally your position at the very end. And I found the B constant, which was used to determine the drag force, by trial and error, trying to get this gravity and drag force line to align with the experimental line that we were found from the video. And once again, the mass was constant. So after applying the 3 datasets to a graphical model here, I noticed that the computed gravity only and the computed gravity and drag force together were almost identical until the very end, where the drag force shows a more negative y position over time. Though drag force increases the overall net force, which makes the object travel further in the negative y-hat direction. When compared to the experimental model, having both gravity and drag forces resembles the closest. In the real-life experiment, error resistant or drag force is also present along with gravity. Some sources of errors here occurred when I was using the experiment, and I noticed that there was an air vent right above the experiment area, and it was blowing air straight down, which could have increased the drag force or the velocity between the object and the air. Also, the lighting of the room could have affected the shutter speed of the camera, which could have caused an unequal distribution of frames as object falls. So what does it mean? The model with gravity and drag force predicts a terminal velocity where the upward drag force equals the downward gravitational force, resulting in 0 net force and no further acceleration of the object, while the motion or the model with only gravity will have a constant velocity because there's no opposing force to counteract gravity. So what if the object was thrown? If the object was initially thrown downward, it would reach terminal velocity faster due to its initial speed, but the terminal velocity itself will be the same as if it were dropped from rest. This is because terminal velocity is determined by the balance of forces of gravity and drag force and not by